Lesson 5. Divergence, Conductor. Section 5.1. Divergence. In Section 2.3, we learned Gauss's law, which states that the electric flux out of a closed surface ES is equal to the net charge within the surface. The law is expressed by this equation. The right-hand side is written in the integral form of the differential charge density ρ dV, over the volume enclosed by the surface ES. From this equation, we can find d from the distribution of charge density ρ. For this derivation of d, we need to know the distribution of ρ inside the volume. Conversely, if d is known, and ρ is not, then how can we find ρ? This is the answer to this question. The del operator is applied to a vector function d in the form of an inner product, and it is called the divergence of d. It is also written in this form. This is another expression of the divergence of d. This is used to obtain ρ from d. For this derivation of ρ, we need to know just local information about d. Let's see an example of how to calculate the divergence of d. In exercise 2.3.1, the flux density d was found to be expressed with these equations, for the charge distributed within a sphere of radius r. The vector r and the unit vector ar are expressed in Cartesian coordinates by these equations. Outside the sphere, d is given by this equation. Then, divergence of d is found to be 0. This corresponds with the charge distribution, indicating that there is no charge outside the sphere. Inside the sphere, d is given by this equation. The divergence of d is obtained as ρ. This result is consistent with the charge distribution inside the sphere. Now let's see what the meaning of the divergence of d is. This is a differential volume dVOL, enclosed by a differential surface dCs, placed in Cartesian coordinates. Its size is dx dy dz cubic meters. In the cube, charge is distributed with a density of ρ coulombs per cubic meter. Gauss's law is expressed with this equation, meaning that the total number of electric flux lines coming out of the differential closed surface dCs, is equal to the amount of charge contained in the differential volume dVOL. This is the definition of divergence of d. It is the total number of electric flux lines exiting a differential closed surface per cubic meter. Let's look at the surface in the YZ plane. Suppose that the electric flux d crosses this differential surface. Then, the number of electric flux going out from the volume through this differential surface is given by this formula. It is negative, because the direction of flux flow in this figure is from the outside to the inside of the volume. Next, let's look at the other surface, which is also parallel to the YZ plane. In this case, the electric flux crosses the surface from inside of the volume to the outside. The change in the x component of d on the surface at x equals dx, from that at x equals 0, is expressed by this formula. Thus, this is the number of flux lines that cross the surface and exit the volume. The sum of the total flux lines, exiting the surfaces parallel to the YZ plane, is given by this equation. By applying the same analysis to the surfaces parallel to the XY plane and XZ plane, we can determine the total number of flux lines that exit the differential closed surface dCs. This is the definition of divergence of d. The numerator can now be replaced with the derived formula. Thus, the divergence of D is given by this equation. The next step is to apply Gauss's law to the numerator in the definition of divergence. Since the volume is infinitesimal, the charge distribution in the differential volume dVol can be considered uniform. Thus, it is obtained as ρ. Divergence of D equals ρ means that the number of electric flux lines generated from the differential cube is equal to ρ. Exercise 5.1. This is your homework. Pause the video, and answer the problem. The author of this material is Takeshi Furuhashi, Professor Emeritus, Nagoya University. If you have any questions, send emails to this address.